This is going to be a presentation of, it's an introductory presentation of the Verilog hardware description language, an overview. The tool, the language as a tool is huge. The language reference manual is more than 1,000 pages. So I'm not going to cover everything, but I'm going to cover more than enough for you to be successful in this lab and also in the next lab for those who are computer engineering majors that have to take ELC 463 next year or in their senior year. So again, we're going to break this into three parts. What I call Introduction to Verilog Part 1, then Introduction to Verilog Part 2. Well, we'll actually do some things. And then Introduction to Verilog Part 3, which we'll do, we'll use some of the parts that we put together in Part 2 and do very simple, but at least a full ALU design. And you'll have a lab to do an ALU in this course. And then we also do an actual real design. So this is actually, I tend to go through it kind of fast because you don't need to know that much even for this course. But it's a good thing if you see it. And better yet, if we capture it in video and you can come back to it and you have the slides, then you can always refer to it. But it gives you a full example of an actual piece of hardware and the levels that you can model and implement in terms of data path, organization, and control with a finite state machine. So it's a good example. Okay, so that's the third part. And again, even though there is a Q&A session at the end, that's not there. I mean, I assume that you're going to be asking questions throughout. So please do interrupt me and let me know if you have any questions, because I cannot look. Even if you write it in the chat box, I cannot look at it until the end. But I will address if you write something there. I think it's just better if you interrupt. So let's get right into it. So Verilog is part of design automation. So it's just one part of what you're going to be doing is the entry. Is the entry of the design into this paradigm of electronic design automation because of complexity. The big part where the productivity comes in is here in synthesis. Here in the synthesis part. What that means is that you are not hooking up stuff or transistors or an abstraction of circuitry made by transistors, which are logic gates. I mean, logic gates that you saw in ENG 312, those are abstractions. There is no such a physical thing as a NAND gate or an OR gate. There are circuits made with transistors that implement that functionality, but that's what they are. So we give them a symbol to that collection of transistors. That is a way of abstracting that circuitry. So we want even to take it one level up, and if we're going to be doing another, we don't want to have to hook up and connect all these gates. We want a tool to synthesize that circuit for us. That's where the productivity comes in. But to have a synthesis tool do its job, for example, synthesize a state machine, instead of you having to hook up the flip-flops and the gates and things like that, you need to put something in. You need to tell it what you want. That's where a hardware description language like Verilog comes in. You're going to be describing the hardware that you want so that the tool can do the synthesis, which avoids you having to do schematics. That's what we want, because you cannot do schematics when you have 20 million gates or 50 million gates on a chip. The other part is that if you're going to be giving this synthesis tool the directive of what to do in the way of the description of the hardware via a hardware description language like Verilog, you want to know if you did it right, if you described it correctly, if your description matches what you want, what you meant to describe. So you need to simulate it. So you need to test it. So that's the other part of the infrastructure. So all that is in Vivado. Okay? Your design entry, your simulation, your synthesis. Okay? We are most interested in design entry, on you writing Verilog to describe hardware, which we're going to be talking about in ELC 451, but also we want you to be able to test your description, so you're going to be simulating as well and showing me that your simulation works. Okay? So schematics can get cumbersome very quickly. I mean, this is just, some combinational logic with a few gates, and already it would take a few minutes. It would take a few minutes to put this together and to hook up everything and to instantiate the gates and plop them in the canvas and draw the lines and things like that. It would take a few minutes. But it may take 10 seconds in Verilog because the description of this could be a couple of lines. So again, that's another level of productivity. Never mind the fact that the tool is going to synthesize the actual logic circuit for you. So we want to get away from this. We don't want to do this. So what is Verilog? It is as I mentioned, is a textual way of entering the design, but at a functional level. Okay? There are two main hardware description languages used in the industry, and they are used about 50-50. Okay? Verilog is one. The other one is VHDL. There is almost like a preference war about them. They do the same things. VHDL stands for VASIC, Hardware Description Language, and VASIC is another acronym. So you have an acronym inside another acronym, which is Very High Speed Integrated Circuits. Now, in my opinion, and why we do Verilog here is because Verilog is easier to understand. The origins of Verilog are commercial in nature. There is a lot of syntax that is similar to C-like, and also syntax that comes from another language that was used to teach computer programming called Pascal. Nobody uses that anymore. But VHDL, as opposed to Verilog that came from the commercial side of industry, VHDL came from the military side of industry. Okay? So it's a little bit drier, and the syntax is harder to grasp. And it's patterned after a language called Ada that was being used in the military to code software systems for military systems. So that's sort of a history there. So Verilog is easier to learn, and once you know Verilog, actually you can pick VHDL much easier, okay, if you ever wanted to or needed to. So it's a good choice to start there. The point is that it's an actual hardware description language used in the industry, and there is like a 50-50 share of each. So you're really not losing anything. So let's look at how this thing looks. If you are describing hardware, you can always put a boundary, sort of like a fence, around the functionality that you want to define and call that a module. Okay? Just like if you were doing some things and putting together some type of prototype, and you were buying these little modules from um, Adafruit or SparkFun or whatever, you buy these little modules and you connect them together. So hardware, you define at some level modules. That is the workhorse of the description. Everything is a module. Now, modules can have other modules inside, right? And modules can be inside other modules that are bigger in functionality. So there is also a hierarchy. A hierarchy that can be logical in nature, but it also represents a physical hierarchy. So you may have a breadboard that has, 3 little modules, or you can put 3 breadboards together to make like a bigger system. So there is hierarchy. The other part is that modules communicate and interface with other modules as part of the system that they reside. So modules have to have ports. And normally ports can be inputs or they can be outputs. So let's look at this description of a module that does ANDing, and it has 3 ports: X, Y, and Z. And X and Y are declared as input ports, and Z is declared as an output port. So we'll go back to all of this in more detail, but just so you haven't seen before Verilog, this is how it looks. And then you have to describe the functionality of the module. So we're saying that this is a 2-input AND gate, okay? So we say that the output C is equal to the ANDing of the inputs X and Y. So obviously, this ampersand is the AND, logical AND operator, and this is an assignment. Assign the output C as the ANDing of X and Y. So you describe the functionality, okay? So that's just a quick preview of a lot of stuff that we're going to be discussing. So some background. So it is a standard. And you can really describe hardware from very abstract level to very concrete levels, and we'll go to the different levels of abstraction that you can use in Verilog, and I'll tell you the one that you need to use in this course, because here we're going to be actually developing hardware. So there is a level, there is an optimum level of abstraction that you want to use, because if you describe at too low of a level, you're not taking advantage of the synthesis tool and you're not getting the productivity. If you describe it at too high of a level, frankly, there is so much that the synthesis tool can do. There is such a thing as a non-synthesizable Verilog, which is very high level of abstraction. And you can use that to still do modeling of systems, but you have to know that it's not synthesizable. And you can use it on things like test benches, because your test bench, where you test where you are designing and describing to be synthesized, your test bench doesn't need to be synthesized. That's just an abstraction for you to test your model. What you want to synthesize is the model. Okay? So there you can be as high an abstraction as you can. And there are some very high level constructs. So some history that I'll go through rather quickly. So it began as a proprietary hardware description language promoted by Cadence. So Cadence is still around, right? So we use OrCAD in our circuits, and they do all kinds of electronic design tools. And then eventually that was transferred to a consortium. And from that, it became an actual IEEE standard. So that's a good thing. Quite a few years ago, and the standard has been evolving, beyond the year 2000, and now we have things like System Verilog, which actually you can use it to describe very high level and complex systems, and there is also something called System C that is competing with System Verilog. But we're really sticking with, for the purpose of this course, Verilog is what we're using. So just to recap, it's all about productivity, getting away from schematic capture, and not only that. Historically, if you were capturing schematics in a tool, let's say like the Xilinx design system, let's say Vivaro, right? If you did a schematic there, that was proprietary. That description was proprietary to that company, because they don't want you to take your design and use it in a competitor's FPGA, for instance. There is a way to transfer schematics, actually. There is a language called EDIF, which is the Electronic Design Interface Format. It actually doesn't work very well because schematics, they are graphics, there's so much detail there, and redundancy. So it's great that Verilog is a standard. You can take your same Verilog and target a Xilinx FPGA, or you could target an Intel FPGA, okay, without having to redo your design. So that design portability is a big advantage of using a standard hardware description language. And again, you can use it throughout your flow of design to enter your design, simulate your design, verify your design, and there are many levels of complexity, as we'll see. So how is it used? At a very high level of abstraction, you could use it to specify things. And then you can capture and verify your design, even document the design. You're going to be working with these two, the capture and the verify. So you're going to be capturing functionality and test benches to verify that functionality. As you go through the tutorial in your first lab, you're going to see a flow very similar to this. This is a simplified flow of what you would follow to design a chip or an FPGA. You would enter your design where you're trying to synthesize, and at the same time, you would develop the testing. You want to be able to test all the features that you're putting in here and know that what you are capturing is what you meant to capture. Beyond not having a syntax error, we're talking about actual functionality issues. So you would use your test bench and your design description in a functional simulation. You're going to be doing all that. And once you simulate and you verify that your design is functional, that you have no bugs, you will synthesize it. Now, at that point, that synthesis step with other constraints, another part of the design entry is to have constraints for the synthesis. You could tell the synthesis, this is my functional description of the design, but I want it to run at this speed. Or I want it to have no more than certain area or certain level of complexity. And I don't want it to go above this much power. So power can be also a constraint to the synthesis tool. So the constraints over here with your clean post-functional simulation design through this path goes into the synthesis tool. Once you synthesize, that's the logic synthesis part, you map it to an actual physical device. In the case of a Xilinx tool, it would be a Xilinx FPGA. And depending on the technology and the chip that the chip has been fabricated, you are going to get actual timing now that this design takes to run, to execute, to actually do its hardware job. And you can get timing data which you can use in a timing simulation, which is different from a functional simulation. The functional simulation step answers the question, does it do what I want it to do? The timing simulation answers the question, does it do it with the level of performance that I want? And you can do timing simulation of the functional simulation, but there are better ways, called static timing simulation. Mainly if you're doing synchronous design, which is what you should be doing anyways. So that's part of your testing as well. Once this is clean, and you can even regress your functional simulation with timing, once all this is clean, then you can, from device mapping, actually transfer that functionality and get your device done. Again, if you're doing an FPGA, this is just downloading what is called a bit file to the FPGA, which basically tells the FPGA how to route the signals to get the hardware functionality that you meant to designing here. But if you were doing like a full custom chip, this step really is huge, right? You have to generate masks, you have to do geometric verification, you have to do layout versus schematic checks, and all kinds of things. But you have to do reliability checks for things like electromigration and things like that. But again, this is very simplistic. The design flows are much more complex than this, and I'm not mentioning a lot of them, but this gives you an idea, mainly in the context of what you're going to be doing in Lab 1 and with Vivado. What you will find is that you can use different design approaches with the hardware description language. You can do top-down design, where you start describing the functionality from the top of the functional hierarchy, assuming that you have the lower levels, and keep traversing that hierarchy down until you get to the leaf type of functions. And that way you can use what is called libraries of these well-known, proven modules or circuit elements. So that's how you should approach it, because you're not going to be developing libraries, which would be the bottoms-up approach. You're going to be assuming that things are there and then just traversing the hierarchy all the way to the leaf components. So I already talked about the ability to synthesize and the flexibility and the portability. So let's keep going. Now, another thing that I wanted to mention is that this type of logic simulation, where you are really abstracting the transistors, as opposed to something like a SPICE. Imagine if you had to do billions of transistors or gate type chips with things like SPICE, it would take forever. the type of simulation that we do with the logic simulator is the switch level simulation, where being that you are simulating logic, that something just happens on the transitions. If the levels are static, nothing is changing. So you can zip through the time and just get to the next transition. That speeds the time of simulation a lot. And as you'll see later, we call that event-driven simulation versus a time mathematical type of model and simulation like a SPICE, where you are constantly with a time step, a small time step, evaluating sort of a Newton-Raphson type numerical analysis technique to solving the system of differential equations. That's the way that SPICE abstracts things. So much faster, and that's great to be able to get feedback on your design, be able to fix things and come back and finishing your work. Okay. So again, all about productivity there. What you see with what we're going to show you here, you'll see that it's easy to actually get started. You'll be able to do things, and you'll be able to do pretty complex things in this course. Like I said, you'll do a couple of processors, sort of a small processors, but with all the functionality there. And you'll be using just a subset of it, which is what I'm going to be showing in this presentation. And then as you need to, as you grow, you can pick up more functionality. So things like libraries, how you package libraries, how you protect things, how you do use the APIs. So Verilog has interfaces where you can actually augment and modify the language itself via C programs. So you can actually expand it. So those are more advanced things. We're not going to cover any of that, but just the introduction that we're going to give you will be enough for you to do some very interesting projects in this course. So let's start with an example. An 8-bit comparator. Okay, an 8-bit comparator. And the way that's going to work is that this 8-bit comparator has 2 8-bit inputs and 1-bit output. And the specification of its functionality is that the output is 1 if the inputs match. It is 0 if the inputs differ. Okay? So, how would we code that? You can start by visualizing that module, right? That comparator, getting the 2 8-bit inputs, okay, and having the 1-bit output. And let's say that in this table here, if both inputs A and B were the same like this, then EQ would be 1. If any pair, bitwise pair, does not match, then EQ would be 0. So that would be a comparator. The code for that comparator would look like this. And from now on, everything that is in bold blue is part of the syntax, is a reserved word of the language, and you should not use it for anything, like names of anything. So the actual syntax, the syntax of the language from now on is going to be in bold blue. So you start with a module where you give it a name, So this is an arbitrary name that you pick. And then a list of the ports. And most lines end with a semicolon. Then you declare the direction of the ports. Input, so A and B are going to be inputs, and you also declare the width in bits of the ports. So the width and the indexes of these ports are going to be 7 down to 0. So we usually do that because we like that the least significant bit is 0, okay, as an index. And then the output is EQ. If you don't specify a width, then it's assumed to be 1. So EQ is 1 bit. And here we have the functionality. Assign EQ equals A double equals B. This is a logical expression that compares A and B. This returns either true or false. If this returns true, EQ gets true, which is 1. If this is false, EQ gets false, which is 0. And boom, you have your functionality. How easy was this? This is just... Now, can someone tell me, if you're so inclined, what would be the actual logic circuit? Can you visualize the logic circuit for this? How it looks? Anybody wants to tell me? So to make the bit-by-bit comparison, right, for each of this comparison, bitwise, you would use an exclusive NOR gate, because it will give you a 1 when they are the same and a 0 when they're different. That's what the exclusive NOR gate does. So you would need 8 exclusive NOR gates. But then you have to aggregate the outputs of those exclusive NOR gates and aggregate them into 1 bit. So that would take an 8 input AND gate. So you could visualize this as 8 exclusive NOR gates of 2 inputs each, taking each of the respective bits this way, and then the output of those 8 gates going into an 8 input AND gate, and if they are all 1, meaning that they are all the same, then the output that goes to EQ will be 1, and that's your functionality. So that's the circuit. 8 exclusive NOR gates, 1 of 2 inputs each, 1 8 input AND gate. So if you could visualize the drawing of that, how much more difficult and time consuming that would be to draw that from a schematic perspective, you know, putting all the gates and connecting all the wires and all that. Now, what happens if I told you that I want to change this circuit that is no longer 8 bits, that the inputs are 64 bits each? Now you need 64 exclusive NOR gates and 1 64 input AND gate. You see the problem there? How do I change this to handle 64 bits? I just have to change that 7 to 64. That's it. And I synthesize, and wow, I got my 64-bit comparator instead of an 8-bit comparator. I'm sorry, I just have to change the 7 to 63. That's the right number. So, hopefully this brings home the advantage of the power of this technology. So what have we seen so far? Every Verilog design has at least one module construct. That's the main description of anything. And your design is going to have many modules that can be connected, and you can put modules inside other modules. Now, when you put different modules connected together, they have to interface via ports. So the ports are important. That's the other part. And we can see that in the description. Okay? Now let's talk about data types in Verilog. Because data types really is an abstract way of representing data, but you have to keep in mind that at the end of the day, everything that we have are bits. That's all. And a bit is an actual wire that is going to be some low voltage or some high voltage. These days, that low voltage is 0 volts, that high voltage could be 0.9 volts. Okay? So we also talk about buses. So we can have wires, or we can have collection of wires, which we call buses. So let's look at data types again. Now, data types we're going to break into two groups: nets and registers. The main idea here is that nets are like real wires running in a circuit. And don't worry too much about this tree, because we said we'll focus on the main things that you need. Just focus on the wire. That's what you're going to be using. And a wire, just like a wire in a real circuit, is continuously driven. So it's connected to some driver. So when the driver changes, the value of the wire changes instantaneously. Okay? There is also a restriction that says that the left-hand side of a continuous assignment, and continuous assignments, as far as we're going to use, is the assign. You're going to be using the assign a lot. The left-hand side of a continuous assignment has to be a net. And for you, that means a wire. Otherwise, the tool, because you are assigning, is like connecting something. Connecting that net to a driver, to a real voltage driver. So it needs to be a net. You can have unconditional assignments, which you have seen already. Okay? For example, data is equal to some data in. Or you can use this syntax for conditional assignments. Okay? So if this, in this case, enable is true, if that expression is true, this goes to data. If this is false, then this goes. We'll talk some more about the description of literals or constants, but we'll see this expression to describe bits or collection of bits. We're going to see a number, an apostrophe, a letter, and a constant value, which could be 0, 1, or Z. Z means high impedance, an open, an electrical open. So remember that we're dealing with hardware, so we have this way of modeling these things. The first number is the width. And then what comes after the apostrophe is the number base. You could have B for binary. You could have O for octal. You could have H for hexadecimal. Or you could have D for decimal. And then the value that comes after is the actual value. But we'll come back to that, okay? With ones and zeros. So that is the first group, the nets. The other group is of data type is registers. And register implies some type of memory. It represents storage. There is the ability to store the last assigned value. And we call that those regs. The word that we're going to be using, as in here, reg, to declare something as a register. We're going to see that the left-hand side of an assignment in a procedural block as opposed to a continuous assignment, and we're going to see what the procedural blocks are in the syntax. We have the rule that the left-hand side of an assignment inside a procedural block has to be a reg. The at is the most used, in fact, what we're going to see as the always at is the most used procedural type of block. So what type of, here we're declaring signal as a reg, and we have this syntax, add posH clock signal equals 1 take B1, which means binary 1, okay? posH means that we are saying that this happens and is sensitive to a positive edge of some signal, in this case clock. We have that ability to make that assertion because this is a hardware description language. If we don't specify something like posH and we say at reset, then this is sensitive to both edges. And that's the most sensitivity that you can have. You can only be sensitive to the events of edges because this is for digital systems. Nothing happens when the signals are quiescent, meaning that they're not changing. Nothing happens. Things only happen when things change, when there is a transition. So here you will be looking at both transitions. So whether reset is going low to high or high to low, at that point signal is going to get a 0, a binary 0. So we'll come back to some more examples, but these are the two big groups of data types. Now, how do we break this a little bit more into something that we can use? What if we wanted to represent a bit? Well, there we have 1, 0. We already talked about Z, that's a high impedance, and then we have X. X is an unknown. In your simulator, X's are going to show as red. And if the simulator doesn't have enough information to resolve a value and come up with an actual 0 or 1, it's going to throw you an X. It says, it's X, it's unknown. That's your first step to start looking for a bug that you have in your design. You should have no X's. So for bits, we have things like we have seen before, 1, binary 1. How about more than 1 bit, like a 6-bit value? Well, we have 6, that's the width, binary, 101001, right? So this number happens to be 41. I could have said 6D41 or 6H29. So this is always the width of the actual bits that matches the width of the declared data. This is the base in which this value is represented. Okay? How about booleans? We can use bits for that. We have integers in Verilog. We have real. And we have time. Now that's a new one. You don't see that in a programming language. We have time. Why? Because we need to simulate. And simulation is done through and against time. So your test bench, you're always going to have this directive as the first line. Backtick time scale 1 nanosecond, in this case, I mean, it can be different units, slash, in this case, 1 picosecond. The first number here is that you are declaring the unit of time that you're going to be using in your design. And this is the resolution, which often the simulator uses as the minimum time step. Okay? Not the maximum, because it's going to go as fast as it can when it can. And then we have this. Then we have this character, pound. Pound is a schedule operator. That means pound 6, if I have this as the first line of my file, and somewhere later I have this line, pound 6 Q equals 1B1, when I simulate that, and the simulator encounters that line, is going to look at this as schedule operator, and the simulator has a now time. That's what it is during the simulation. There is a now time, what the simulation time is. So it's not going to execute or assert this at that time. It's going to schedule it for the future. How many time units into the future? 6. What is the time unit? Nanoseconds. So in the simulation, Q becoming 1 is not going to happen at this time of the simulation. It's going to happen at now plus 6 nanoseconds. It's going to be a schedule. That's useful for constructing test benches where you have to manipulate waveforms. So going down the line, how do you handle registers? Well, a register, it could be a single bit or it could be an array of bits. How do you handle characters? Well, that's an 8-bit register. How do you handle strings? Well, that's a very long register that has 8 bits times the number of characters for the length. So you can, you can get around some of the restrictions and handle a lot of things. Let's talk about design units. This is really talking about libraries, so I'm going to go fast through it. You're not going to be using any libraries, but do know that they're widely used in the industry as a way to leverage and reuse proven units that have been designed before. You no need to reinvent the wheel. So I'm going to keep going through this. Now this is very important. The levels of abstraction in Verilog that are tied to the styles. The key here is to recognize that this different levels of abstractions or styles, the difference is how closely they reflect the actual hardware. At some point, you could almost describe a schematic in a textual way. And actually, Spice has that ability. Originally, Spice, there was no graphics, and people could not even draw a schematic. They would actually describe the schematic with Spice in a textual format. That's still available. But that's a very low level. We're going to see when it is appropriate to use that. And there are other levels. We're going to talk mainly about three levels: behavior, data flow, and structure. That structure is the lowest level, which you're really connecting things. And there is a place for it. We'll get to that, because we'll start at the top, behavior. Now, behavior, there's really no restriction in describing behavior, because the language has very powerful set of syntaxes and constructs. There is something in the middle where you actually are indicating more than the behavior, but also the data flow without quite getting into the structure. That's somewhere in the middle here. Now, even though I don't have it here explicitly, there is a level right between behavior and data flow. It's higher than data flow, but not completely open-ended that just the behavior is captured. You're capturing a little bit of data flow as well with some behavior. So somewhere in the middle. So it's higher than data flow, lower than behavior. We call that synthesizable. That's what you're going to have to be writing. It has to synthesize. And the examples, and mainly the examples that we use to conclude this presentation, which we'll do probably like in 2 weeks from today, are going to be key for that. You have to have behavioral for your design, synthesizable, Verilog. Now for the test bench, you want to be all behavior, because you're not going to synthesize your test bench. You're not building the test bench. You are using the test bench to test what you are building, what you want to synthesize. So that's an important distinction. So as we go from a structure to behavior, you can think of all these examples of representations, physical information, hierarchy, Boolean equations, arithmetic, assignments, register transfer, state machine, sequential description, test benches, and a specification. So it goes from a very low level of abstraction where you have the actual physical information, how things connect, specific things or devices, to just the specification. That's the highest level. Let's do a quick example of something that I would consider behavioral, even though it's simple. Okay? And again, between behavioral description and lower level, the main thing is the concept of timing. That behaviorally you focus on the behavior without caring about the implementation, which is very tied eventually to the timing between events. Let's say you wanted to have a behavioral model of a half adder, okay? And we all know how a half adder looks, okay? We have two 1-bit inputs, and we have a sum bit output and a carry bit output. If you were going to do the schematic, it would look like that, okay? So this half adder, behaviorally, we could code it this way. We have the name of the module and the ports, the inputs here, they're all 1 bit, the outputs. I'm going to come back to this. But here's that procedural assignment. Always at can you all still hear me and see me? Because I got a notification that my internet connection is unstable.
Yeah. Yeah.
Okay, great, thank you. So always at A or B begin, and this block is closed with the word end. So begin and end are used to enclose groups of statements, just like the curly brackets are used in C++. Because these are groups of statements, these are procedural blocks. Then sum is equal to A exclusive OR B, so this is the exclusive OR operator, and carry is equal to A and B, and then end module. Now, output, sum and carry are outputs. And here, we are recasting sum and carry as regs. Why are we doing that? Well, remember, wires and nets versus regs. The ports of a module. Which part?
Part where you're talking about where we're recasting sum and carry as reg.
Right. So here we are recasting the outputs, sum and carry, and reg. And I want to take you back to what we were discussing and the distinctions between nets and regs as data types. The ports of a module are nets. However, this is a procedural block. And we said that the left-hand side of assignments inside a procedural block need to be regs. That's why we are recasting these outputs. Otherwise, we will get a syntax error. So something to watch out for as you do your own models, okay? So this would be a behavioral description. Simple example. All right, so I'm going to stop here and ask if there are any questions.